Alright, so again, just to recall, a separable differential equation is something that can be expressed as the product of a function of x and a product of a function of y. So in order to be able to start this problem, you need to take the dy dx equals negative 2xy squared, and you need to isolate it so that the y's are on one side and the x's are on the other. So your first move should have been to divide by y squared so that you had the integral of dy divided by, and I moved my negative with it, but you didn't have to, so you could choose to keep your negative on either side. And then I moved over the dx, giving myself the integral of 2x dx. By putting the dy's with the y's and the x's with the x's, we can now integrate because we have like variables with the correct derivative integration constant. So if you think about y squared, this is the same as negative y to the negative 2. And then over here, you could bring out your 2, leaving you with x dx. So you integrate both sides of your function. So you're adding 1, so you get negative 1. And this is why I brought over my negative, because when you have a negative and then you have a negative exponent, the negatives end up canceling. So by moving my negative with me, I've canceled the negatives out. So I have y to the negative 1 equals, and then you get 2x squared divided by 2, so the 2's are going to cancel. So I have x squared plus c. So we have y to the negative 1 equals x squared plus c. Well, that's the same as saying 1 over y equals x squared plus c. But we know that when we talk about functions and we talk about problems, we don't talk about 1 over y. So what we can do is we can flip both of these so that it becomes y equals 1 over x squared plus c. And then what we could do is use our initial condition. Yeah.
So when you integrate y does y get it?
Because you only need one constant of integration. It wouldn't have mattered what side I put it on either. Okay, so then using our initial condition of y equals 2 and x equals 1. And here's the thing, too. You could actually do your initial condition wherever you wanted to. You could have plugged it in here or over there. So plugging in y equals 2 and x equals 1, you get 2 equals 1 over 1 plus c. So again, working backwards, we have 2 equals 1 over 1 plus c. So we're going to flip them. So you get c equals negative 1/2. We know we don't like fractions and fractions, so you're going to multiply everything out with 2. You get y equals 2 over 2x squared minus 1. Yep.
How do you want to integrate that with negative y to negative 2 dy?
The power rule. So you add 1. No, because dy is just the, like, dy is like dx. It's not a function. It's telling you the constant of integration. So again, that leads us into 6.4, which is exponential growth and decay. So we know that there are many, many applications of calculus outside of the calculus classroom. We've seen most of those applications in terms of physics. So we've seen them with like position, velocity, acceleration. Well, they also can take on forms that happen in like biology or happen in terms of maybe even chemistry. So there are many applications that the rate of change of a variable and its proportion to y can be applied using calculus. So if y is a function of time t, we can express this as the following statement. So if you think back, we used to have this statement, and it was dy dt, where we're talking about y with respect to time, equals constant k times some function y. And again, it's important to understand that k is a constant. So if k is a constant, it's just a coefficient. It's a variable. Again, it has that application where you could bring it out in front of the integral and it wouldn't affect what you were integrating with respect to. So let's take, for example number 1. It says find the solution to the differential equation with the given initial condition y equals y naught when t equals 0. Why is that important? Well, that y equals y naught when t equals 0 allows me to solve for c. So essentially what we're doing is we're integrating the previous function. So we're going to integrate dy dt equals ky using these initial conditions. So once again, in order to integrate this function, we have to change our variables around. I need to divide by y, so it's over with the dy's, and I need to multiply by dt, so it's over with the k. So dividing by y gives 1 over y dy equals k dt. So integrating both sides to get rid of the dy and dt, 1 over y dy becomes what? Natural log. Hence, exponential growth and decay. We have a natural log. And then we get kt plus c. Because again, k is a constant, so it's like the number on the variable. So you get kt plus that constant of integration or placeholder. We don't like problems to be ln of y. We like them to be y equals. So how am I going to eliminate the ln? E both sides. Let's go back to rules of exponents and variables. If I have x to the m plus n, what's that actually equal to? X to the m times x to the n. Why would that be helpful here? Well, right now we have kt plus c. So I have two things being added in that exponential top. What we can do is we can treat that like e to the kt times e to the c. Why is that helpful? What does e raised to the c give me? A constant, which represents a number. So I don't have to treat this like e to the c. C itself is the constant of integration. It represents a number. So what we can do is we can say, oh, well, this is actually y equals c, because e to the c is a constant, and I don't know what c is, so c is a constant of e to the kt. So anytime I integrate this function of dy dt equals ky, this c right here is the same as y naught. That c is y naught, or the initial starting amount. Why is that super, super important? Where does that help me? Well, that helps me once I start to get these numbers and I plug them in. Yes. So what do I know? Well, I know that at time t equals 0, y equals y naught. Can you see how that is true? Because I just said c is y naught. If you plug y equals c e k times 0, k times 0 is 0, e to the 0 is, so you get y equals c, which equals y naught. We don't know what y naught is, but we know that no matter what it is, y equals y naught. Therefore, we have our lovely y equals y naught e to the kt. This function right here represents the initial condition y naught, e to the kt, where this is the exponential growth or decay, and y is where you are. So again, this is our most basic formula for exponential growth or decay. We don't know if it's growth or decay because we don't know if k is positive or negative. A positive or a negative k would tell me my growth or my decay. So putting that into words, if y changes as a rate proportional to the amount present, then dy dt equals ky, and y equals y naught. When t equals 0, then we have this equation, y equals y naught e to the kt. And again, like I said, if k is positive or greater than 0, then you have growth. If k is negative or less than 0, then you have decay. So example 2, it says the rate of change y is proportional to y when t equals 0, and y equals 2, and when t equals 4, or t equals 2, y equals 4. It's the value when t equals 3. So, what do we know? Well, we know because of this statement right here, we're using this idea of dy dt equals ky, and y equals y naught e to the kt. So those are the two functions I'm using. What can I plug in? What do we know? Perfect. Y naught is 2, or y sub 0 is 2. We know that from this initial condition right here. You would plug 2 in for y, and you'd plug 0 in for t, so you'd get e to the 0, which is 1, thus giving you y naught equals 2. So now I have a more specific y equals function. I now have that y equals 2 e to the kt. What variable do I need to know or find next? So I have another condition. I have t equals 2 when y equals 4. Plug it in so that y is now 4 and t is now 2. So 4 equals 2e to the 2k. Solve for k. So divide by 2. How do I get rid of an e?
Instead of divided by 2, would you take the log base 2e?
That's easier to divide by 2. Yes. So you have the natural log of 2 equals 2k. Divide by 2. And we get k equals the natural log of 2 divided by 2. Yours would have a log in there. That's gross. You'll never have an AP answer with its multiple choice for D1. If this was an AP like multiple choice, it's going to be LN.
And then could you put that that's your could you put that on the inside and make it LN squared root 2? There's no powers on the inside, give it coach the outside.
Yeah, but watch what we're going to do. So we have y, now plugging in our k, we get y equals 2 e to the 1/2 ln of 2t. So the last question is, what is the value of y when t equals 3? So we're going to bring it up as the next one. So y of 3 would equal 2e to the 1/2 ln 2 times 3, which is kind of like saying 2e to the natural log of 2. So we have 3 halves. But remember, if you have 3 halves out in front, you can bring it up as your exponent. Why is that helpful? Well, what happens to e and ln when they're like that? They cancel, right? So you get 2 to the 3 halves. Now remember a rule, this is kind of like a 1, right? So if you have the same base being multiplied, you can add their exponents. So it's like adding. So you get 2 to the 5 halves. And there's your nice, precise answer. To the 5 halves is like roughly 5.6. Anybody need to go to these to get food? You need to go get coffee? You're like hurt
Yeah,
over
but I
there.
get some coffee.
Okay. All right, example number 3. If dy dt equals negative 2y. So now, instead of not knowing k, we know k. And if y equals 1 when t equals 0, what is the value for t when y equals 1/2? So now when we integrate this, we don't have a k constant, we actually have a k value. So we can take this and say, okay, dy dt equals kt, or ky rather, so that tells me that k is negative 2. So if k is negative 2, y equals 1 when t equals 0. Well, at time t equals 0, we always find our y naught. So y naught is 1. So we know k, and we know y naught. So we know y equals 1e to the negative 2t. Knowing our formulas, knowing what they mean, and knowing what they represent means that I don't always have to integrate. You could have integrated this over here, and you could have said, okay, well, 1 over y dy equals negative 2 dt, and you could have taken your integral, and you could have gotten to this. But if we know what our formulas represent, and we know what pieces mean, now we have our growth and decay equation, and all I have to do is plug in for y and back solve for t. Why is y smaller than y naught?
Because it's decay.
Because it's decay. How do I know it's decay? Because k is negative. So my y is smaller than my y naught, and my k is negative. So that is my way of knowing this is a decay function. So it means whatever we're talking about is getting smaller over time. So we have 1/2 equals 1e to the negative 2t. That 1 really doesn't do anything. So we're going to get rid of the e by ln'ing both sides. So you have the natural log of 1/2 equals negative 2t. So t is equal to the natural log of 1/2 divided by negative 2, or negative 1/2 the natural log of 1/2. Which really the natural log of 1/2 is like saying ln of 1 minus ln of 2, which is really just like saying the natural log of 2. But you could leave it like that. Questions at all on growth or decay exponential functions? Okay, the next part that we are going to look at is going to be on radioactive growth and decay. So we can talk about these types of problems in terms of radioactivity. So the equation for the amount of radioactivity in an element left after time t is still that y equals y naught e to the negative kt. So again, we're talking about radioactive decay, so the equation is given to me as a negative k. What that does is that allows the decay constant k to be positive, and half-life is the time required for half of the material to decay. So we actually are going to get a formula for half-life. The half-life is an important aspect to an element. Oftentimes when it comes to radioactivity, they say that half-life is the point where you can return safely to a site that has radioactive material. So if you think back, there was like a movie called Chernobyl Diaries, and that was a site of nuclear reaction with radioactive decay. They figured out over time when it would be safe, and we're actually going to look at the equation for that. So, yes.
What does the y naught mean?
Like the initial condition. So the y naught represents like what you start with. So if you go back and you even think like to the days, or if you're in accounting right now, or if you're in applied math right now, when you go to the bank and you open a bank account for the very, very first time, you put in an initial amount. So, what?
That's, yeah, your initial deposit.
Yeah. So that's kind of like what the y naught represents. It represents like the initial amount you started with. So, in terms, and the reason I bring up like that bank account stuff is if you think back to compound interest and functions like that, we used to have the equation y equals p e to the rt, where r was the rate of change of the account, t was the amount of time, and p was the amount you put in. So we are actually doing that again, but this is like the bank version. We call this the principal amount.
So that
So it's always just kind of like what you start with.
okay, and then why is our K? Because that equation has the rate positive. Why is our K negative in this?
Because it's radioactive decay.
Oh, it's not, okay.
So it's a decaying function. It's,
okay.
yeah. Yep.
I just need to go back for one.
Why is the initial amount, like, why not being multiplied by the E and stuff instead of added on?
Because the way, like, exponential, and it works, is that you're multiplying by that. And that's what we actually got, that why not being multiplied, came from when we found the C value and brought it out in front.
Okay.
Because it was really KT plus C. But then we said C is a constant, so why not becomes that constant. So what I want you to do is I want you to take that y equals y naught e to the negative kt. And I want you to think about the fact that we want to know the half-life. So half-life would be when we have half of the initial amount. So I want to find the time when I have half the initial amount. So we're going to replace y with half of y naught. Solve for t. So we can find that time. Well, what happens is you would divide by y naught. Y naught divided by y naught goes away. I need to get e gone, so I ln both sides. I want to solve for t. So I divide by k. And this is where I said you would use that property of subtraction. This is kind of the same as saying negative 1 over k, ln of 1 minus ln of 2. But the reason that's so important is the natural log of 1 is really 0. So now I have a negative times a negative, which becomes a positive. So I get 1 over k, natural log of 2. But again, we like to get rid of stuff out in front. So it's really like the natural log of 2. And we could raise it to the 1 over k power. Or you could keep it as the natural log of 2 all over k. And get rid of the fraction out in front. Typically, you're going to see it like this. Because typically, we're going to know what k is. So half-life in radioactive decay is always the natural log of 2 divided by k. Half-life in radioactive decay will always occur at time t equals the natural log of 2 divided by k. So you'll see why in a second here. That's super, super important. Remember, this represents a time. Representing a time. So I brought up the example of Chernobyl. And then I said, hey, we're going to actually look at a problem that involves it. So it says the rate at which the radioactive decay for an element, as measured by the number of nuclei that change per unit of time, is approximately proportional to the amount of nuclei present. Suppose that 10 grams of Pu-239 was released in the Chernobyl nuclear accident. How long will it take for the 10 grams to decay to 1 gram, knowing that they have a half-life of 24,360 years? half-life allow me to find?
Okay.
Tells me to find K, right? So the time is 24,360 years equals the natural log of 2 divided by K. Or rather that K equals the natural log of 2 divided by 24,360 years. What's my why not? What was the initial amount present when the explosive reaction happened? Yeah, 10 grams. So my why not is 10 grams. What am I looking for?
Why?
I want to know y equals 1.
You would find t when 1 equals
Yes. So I want to know the time when the y value is equal to 1. That's the time when it's safe to return. So I have 1 equals 10 for y naught. E, this is decay, so it's automatically negative. My K is ln of 2 all over 2, 4, 3, 6, 0. And I'm solving for T. So you divide by 10. ln both sides. I have a fraction being multiplied by my time, so I'm just going to multiply by its reciprocal. Anytime you have the natural log of a fraction, it's the same as like multiplying or subtracting the top and the bottom. Negatively speaking, anytime you have the ln of 1, you're going to get 0. So if I have a fraction with a 1 in it, it's really just like having negative the natural log of the base. So it'd be negative natural log of 10. So we can rewrite this as 24360 with a negative out in front, natural log of 10 all over natural log of 2. If you multiplied this out, the time it would take to get down to 1 gram is 80,922 years and 2 months. Because this would be like the natural log of 1 minus the natural log of 10. Thank you. What?
So it would never go.
Yeah, no.
He would be gone
No, no.
It'd be on 80,000 years.
Maybe.
I give us 1,000 years.
We won't be like humans anymore.
It's really unlikely we're gonna like survive for more than
Or
that's like the
at least not be
paradox.
human.
We'll be robots. I won't be a robot.
I don't say my
We're just robots right now. We're organic robots. What we are.
What?
That's you.
Yeah.
That's what we are.
Okay. All right. There's one other. There's one other formula we want to talk about today, and that's Newton's law of cooling. Newton's law of cooling says that we can take temperature of an inside and outside surface and find the temperature of the internal surface using that concept. So we have this formula, and it's T minus Ts equals, not the hiccups, T naught minus Ts e to the negative kt. So it's T naught minus Ts now representing your initial area, and T minus Ts representing your other side. So the y has this negative Ts aspect to it, where that Ts is the temperature surrounding the medium. So you yourself are like a medium right now. What is your temperature typically of a human being? 98.6.
I said 98.2. I'm sorry.
And he said 96.5.
Yeah, you know you're kidding.
So
Just a little bit.
a normal human being's body temperature is 98.6.
23. We're talking fall.
So
That's Jason when he's eating too many bananas.
that would be the temperature of the medium. The temperature of its surrounding is the temperature of the room. We typically keep our houses in like the upper 60s, lower 70s, depending on if it's winter or summer.
I'm saving energy right now. I'm at like 40 in my house.
What?
Where Park is.
Your house is in the 40s? There's no way.
No, I'm just kidding. We turn the temperature down to like 50 or something when we leave the house, and we turn it back up.
Yeah, I mean, my house right now is probably set to like 57.
I wanted to get a smart temperature, like or a smart thermostat, but my dad said those aren't good. You know what I mean? Where it's like a thermostat, and
You
it has like
mean the
a
Nest
screen and
Nest
stuff.
thing?
A Nest, yeah.
I mean, I
So with your
have a
phone,
touch
and it
screen.
it's supposed to save money, but it still costs $200.
Well, and here's the thing. Like you can get the panels and you can make a schedule. So like my Monday through Friday is something different than my Saturdays and Sundays. Yeah, because nobody's home Monday through Friday. Well, I'm talking like my whole house, but yeah, we have stuff like that in the kids' bedrooms. Or like the ceiling fans, we change the direction they blow in the winter. All right. So, have you ever been in your house and you have that steaming, piping hot cup of coffee, and you've set it down, and then you walked away from it, and then when you get back, it's cold.
I'll give a Yeti.
Okay, cup. I didn't say Yeti.
Cold does not
They have a
exist.
vacuum in between the space.
Cold doesn't exist.
So, suppose that we have this cup of coffee and it's sitting. And when it first came out, it was 90 degrees Celsius. And then it changed to 60 degrees Celsius in 10 minutes just sitting out in a room that was set to 20 degrees Celsius. In terms of Celsius, your bodies are 37.
I don't care about Celsius.
Okay, using Newton's law of cooling, find how much longer it would take the espresso to cool to 35 degrees Celsius. So let's plug in to what we know. We know the initial condition, which was 90 degrees. We know the temperature of the surrounding space. We know the temperature after a certain amount of time. And we want to find the time for a new temperature. So, let's plug in. We know 60 minus 20. So that's the temperature it is currently in a 20-degree room. The initial temperature was 90 in a 20-degree room. It's decaying, so it's negative K. And the time it took to go from 90 to 60 is 10 minutes. So 60 minus 20 is 40. 90 minus 20 is 70. We want to get rid of the 70 in front of the E. The the 70 and the 40 zeros would cancel. You'd ln both sides. You get rid of the e. So you'd have k equals the natural log of 4/7 divided by negative 10. We could plug that back in and then re-look at the conditions to find when t would be 35. So the temperature of the room hasn't changed. What we want to do now is we want the temperature of the coffee to be 35 in a 20-degree room. His initial conditions were 70 because 90 minus 20 is 70. That's not going to change. E, now we know K, so the negatives are going to cancel. You're going to have the ln of 4/7 over 10 t. 35 minus 20 gives you 15. What's nice over here is if I brought that 10 up as an exponent, I have the natural log of 4/7 to the 10t. So my ln and my e's cancel. So you have 15 over 70 equals 4/7 to the 10th t. No, it's over 10. So do it in 10. I ended up changing it back to L's anyways for my final answer, but if you want to. The only way to get this as an actual number is to use a calculator anyways. We don't know 1/10 powers and we don't know. So using your calculator, you would divide all that and get that t is approximately 27.527 minutes. It's a perfect drinking temperature is what they're saying at 35 degrees Celsius. So if you think about that, like 35 degrees Celsius is probably roughly in the 80s. Yes. But I don't know a coffee pot that's going to spit it out at 90 degrees Celsius. It's pretty hot.
That's fine.
It's like McDonald's. I was thinking about McDonald's. I wish I burned myself.
I typed soup.
Yeah, I was like, what's
It's in the book. I never freeze. I never. Look on the book.
All right. Your homework is in the book. We are on, there's another page and then I actually have it. So we're on page 357. You'll do 1 through 9. So really this is just one to 15 on.